If you started watching this video without watching Cylinder Head 205, you might end up a little bit lost. In 205, we covered all the tools needed for this video's topic and the basics of using them. We also dialed in the camshafts to the manufacturer's recommendations for their opening and closing events. At the beginning of that video, we installed a set of test springs that help us check valve clearance, and they were useful for dialing in the cams, but they're not required for that procedure. You have to use them for checking valve clearance, and I haven't shown the procedure for doing that yet. So that's where we're at right now. My bucket of bolts camshafts are matching what it should be on paper. So it's all good, right? Don't give yourself a false sense of security here. Before we jump in head first, I need to explain what brought us here for the newcomers. This engine's for my Hyundai Elantra. It was gifted to me by one of the most outstanding and brilliant and gifted mechanics I've ever known. Someone who for many years was my mechanical mentor that pushed me to the next level whether he realizes it or not. I'd never have built my first engine if not for his help. I was hungry for the experience and he fed me. It's as simple as that. Years later, he built this car with nothing but factory Mitsubishi, Hyundai, Nissan, and Subaru parts without any of the precision measurement tools that you've seen me demonstrate, and literally butt-tuned about 300 pounds of torque into this car. He did it solely by looking at specifications and figuring out how to make all this stuff work together. Everyone I've ever let drive this car has continually tried to buy it off of me because it's so much fun to drive. Its hideous outer shell is part of that appeal after seeing what it can do. It was a sad day when it blew up, and I had no intentions of letting this car interrupt or bump any of my other builds that were already in progress out of the way. I just wanted to do a quick bearing and gasket set and put it back on the road, but I quickly realized what a lost educational opportunity it would be for everyone else. The part selection he used on this build is so odd and so worn from being installed in no less than 4 of his other builds, or out of my spare parts bin, or wherever we could find whatever it was that needed to be put together to make something work. Well, these parts were repeatedly machined from one build to the next, and so this is a pristine example of what Mitsubishi never wanted any of us to do. Because all the irregularities, and because these stock parts are being pushed to the edge, there's really never been a better example of a car to learn from in my stables. If I just threw a crank, bearings, and a new gasket set at it and ran it like it was, I'd never have the opportunity to show you how to overcome problems you might encounter along your journeys. And you wouldn't learn as much if I had a pile of parts that fit perfectly the first time around. I'm not expecting these kinds of circumstances on the GSX build at all, so I'm using this car as an example for the more difficult portions of the assembly. This video is all about valve clearance, and I'm going to greatly expand on the topic of valve timing as well because it plays a huge role in our valve clearance. Basically, we're going to fish out the rest of this can of worms we opened up in Cylinder Head 205. My test springs are still installed, and we're right where we left off. To test the valve clearance, rotate your crankshaft to 20 degrees before top dead center. Zero your dial gauge and press down on the exhaust valve until it comes in contact with the piston. Write down what it says on your dial gauge. That reading is your valve clearance at that degree of crankshaft rotation. Next, turn the crank 2 or 3 degrees and repeat the same process. Zero, press, write down your results. You can do this without zeroing the gauge every time. You just write both numbers down and subtract the little one from the big one. You want to test 20 degrees of crankshaft rotation in the region around top dead center for your results, or until your valves are well past your clearance specifications. You'll notice that the valve clearance changes as you rotate the crankshaft, and at one point you'll get a tighter clearance result than at any other position on the crank. That's the number everyone refers to when they talk about valve clearance. It's the minimum distance that you can get for thermal expansion and valvetrain deflection before risking contact with a hot, fast-moving piston that's carrying an awful lot of momentum behind it. Tight valve clearance is one thing, but exceeding that valve clearance limit is where things get really bad. Do the same thing for the intake valves. Set up the gauge just like you did when you were degreeing camshafts. Write down your degrees and measurements. Find the tightest measurement, and that's your intake clearance. Just because your engine rotates freely by hand on an engine stand, it doesn't mean that you're in the clear. I've mentioned valve clearance in several other videos, but never covered how to check it until right now. Sure, this process looks a little bit tedious, but how tedious is rebuilding an engine with a perfectly good timing belt still attached to it? Really, this is very simple. The tools are cheap, and if your engine's on the stand and you're degreeing your camshafts anyway, you really have no excuse not to do this. Depending on where you set your camshafts or which ones you choose to run in your engine, your valve clearances will change. So if you're going to do the rest of this job correctly, check your valve clearances afterwards. It's just an extra step to perform, and it really only takes a few minutes to make sure everything's kosher. The peace of mind it yields the first time you pray for fire and hit the key is worth all of this effort because you know beyond all shadow of a doubt that you won't have any interference problems. So doing this test on an engine stand avoids all of those expensive and time-consuming consequences should you find that you do have a problem. The measurement you want to shoot for here is greater than 80 thousandths of an inch on the intake valves and greater than 100 thousandths on the exhaust valves. For you non-imperialists, that's 2.03 millimeters on the intake and 2.54 millimeters on the exhaust. If you're using an aluminum rod in your build, it needs a little bit more, and you should check with your manufacturer for those recommendations. If you can't achieve these results with your part selection, and if you didn't take measures to correct it somehow, then you just built a grenade with a really short fuse. You can see here that a grenade is exactly what I've built. I don't have adequate exhaust valve clearance. I've got my cams dialed into the manufacturer's spec, but this head was decked way too far for this to work like this. If this is the reason why you're watching this video, because this sort of thing has happened to you, then you're about to be really happy with where this video is headed and glad that you clicked. There are several different ways to deal with this problem, and I'm going to talk about all of them. To illustrate this as best I can, I want to talk about the basics of valve timing events and what goes on inside your combustion chamber. Since I can't show you the inside of a running engine, I had to draw this to illustrate my points about valve timing events, cylinder pressure, valve train behavior, and RPMs. Let's start with the camshaft basics. There are several characteristics ground into your camshaft profiles that you can easily identify. One is the base circle. That's the point around the camshaft where there's zero lift. The lobes protrude from the base circle. The flat regions of the lobes are called ramps. The top radius is called the nose. The center of the nose is where max lift is achieved. The height of the lobes and the shape of the ramps ground into the camshaft regulate when and how aggressively the camshaft opens and closes the valves. The lobe center line is the imaginary line between the peak of the lobe and the center of the base circle. You can locate the lobe center line by doing a little bit of math from your degree wheel. First, you find your valve opening and closing events and add 180 degrees. This gives you your duration, which represents in crankshaft degrees how long the valves are open or above zero or at a given lift. If you divide your duration by 2, you get the lobe center line of your cam grind. If you then subtract each open or close event near top dead center from each lobe center line, then you get your installed center lines. Normally your intake opening event is before top dead center and your exhaust closing event is after top dead center. If they're on the opposite side of top dead center than where they normally would be, then those values are negative, so you would subtract a negative number to get your installed center line. In other words, you'd add them. Subtracting a negative is addition. I don't have that issue here. Both of my events are at 2 degrees, so the math is really easy. Basically, half of your duration minus the events from top dead center is what the center line represents. If you check these values against your degree wheel, you'll find that the point where you measured max lift should be the exact numbers we just calculated. The installed center line is one of the means of referencing the camshaft's characteristics. Center lines don't tell you everything you need to know, though. There's another specification that once you have your center lines, you're able to calculate. It tells you how these bump sticks are going to behave. It's called lobe separation angle. Lobe separation angle is the number of crankshaft degrees that separate the center line of the exhaust cam from the center line of the intake cam. That's all it is, and it's usually a number between 102 and 122 degrees. To get your lobe separation angle, add the intake and exhaust center lines together, then divide by 2. This is the number that gives the most information about how my engine is going to behave with these particular timing events. The center lines on these cams are very close together, meaning that the maximum lift occurs in the fewest number of degrees that you would want to aim for on a 4-stroke engine. Some people use general terms like tight and wide to denote where in that range the lobe separation falls. That's fine, so will we, it makes sense. Their meaning is pretty clear, and you'll see that here in this example. This is what they mean by tight and wide. With the tighter lobe separation angles, you can expect to find a shorter torque curve with a higher and an earlier peak. The power band will be shorter, produce more compression overall, offer more scavenging from overlap, which we'll cover in a second. It'll reduce vacuum and idle stability while increasing all of the conditions that contribute to knock. Look what happens when you increase the lobe separation angle. You broaden your torque curve, reducing overall torque output. You decrease your overall cylinder pressure, compression, and overlap. You lengthen your power band, increasing idle stability. You increase vacuum and valve clearance, but the engine will be less powerful, more tame, and less likely to knock. It makes a milder, more streetable tune. That's not what I'm going for at all with this build. I like that back the other way where it was. There, that's better. You can find good and bad characteristics on both sides of the spectrum, and lobe separation will determine on which side of the spectrum each of these factors lie. I put these bullet points in the description for reference, so you won't need to watch the whole video again to find this. To turn the rotating motion of the camshaft into linear lift, a dual overhead cam 4G63 has roller rockers. These roller rockers use the ball end of the hydraulic lash adjuster as their fulcrum point. And on the other side of the roller, the rocker rests on the tip of the valve. The roller follows the face of the cam lobe until the ramps come along, pressing down on the rocker to open the valve. It acts as a lever and produces a lift ratio of 1.7 to 1. What that means is the rocker makes more lift than the size of the cam lobes. It's 1.7 times longer from the pad to the fulcrum than it is from the roller to the fulcrum. So if you wanted to calculate how much lift you'd get out of any camshaft, you can measure the lobes at their highest point and measure the base circle. Subtract the base circle from the lobe measurement and multiply by 1.7. If you change the amount of lift your valve train generates, you also change when the valves are at a given depth, as well as how fast they're traveling to get there. There are conditions in your valve train that can contribute to catastrophic failure of your rotating assembly, despite the fact that it rotates freely on an engine stand. And we're not just talking about thermal expansion here. That's definitely a factor. But I'm talking about physical events in the valve train that once the engine's assembled are basically invisible to you. Let's slow this down so you can see it. The worst thing that your valve train could experience is valve float. When a valve floats, that means the cam lobe loses contact with the rocker, and this results in the valves closing later and harder, and with much greater deflection. At RPMs higher than your springs can handle, the lobes slapping the rockers to open the valves can overpower your spring's ability to recover from it, or to close properly if they don't have a high enough spring rate or seat pressure to handle that rotational speed. Another condition is called valve bounce, and you can see it here. It's a vibrating effect that can occur in a loose valve train after the valve slams shut, or when the seat pressure isn't correct for your conditions. Even if the on-time piston manages to miss the late valve, either of these conditions wreak havoc on the valve guides, seats, springs, retainers, rockers, and cam lobes. It's imperative that you have all of the right pieces working together for your conditions. Valve float and valve bounce can be caused by too weak of a valve spring for your application, too aggressive of a ramp angle on your cam profile, or too heavy of a valve assembly. But the one thing that causes it the most is a right foot. Right foots break more engine parts than anything else in the history of mankind. Watch out for those things. Rev limiters exist for a reason. Here we are at top dead center. Notice the intake and the exhaust valves are cracked open just a hair. It's because the intake valve opens at 2 degrees before top dead center and the exhaust closes 2 degrees after top dead center. This provides 4 degrees of a condition called overlap. At low RPMs, a car with lots of overlap will idle poorly and suffer in part throttle performance. But overlap isn't all bad. Boy, does it love that right foot. It's a different beast when the engine's revved up high. It improves airflow through the ports and improves throttle response on turbo cars because it offers a slightly quicker spool up as a result. Overlap at high RPMs helps scavenge the combustion chamber of impurities, making room for more air and fuel. It also helps minimize some of the compression forces that can contribute to harmonic vibrations in the bottom end. It just comes at the sacrifice of using a little bit of the stroke that would normally be used to compress air and fuel, and therefore lowering your final compression ratio. So it has a limiting effect on your engine's potential. It also lends to creating that nasty, lumpy sounding idle at stoplights that so many people like. You know, the one that makes old people show their age. But you can overdo it. Overlap has a sweet spot. Too much of it can be a bad thing. The usual side effect of installing longer duration cams is increasing your overlap. If for any reason your engine's valves open or close earlier or later in relation to your crank's rotation, or if your overlap increases, then the events at top dead center really need to be scrutinized in relation to your valve clearance. When overlap increases, not only your compression, but your valve clearances also decrease. This cam combination was selected specifically because of its tight overlap characteristics. I want to use as much of my static compression ratio as I can, so I selected these cams. Most camshafts, including factory cams, have more overlap than these, but these are my example. I did this to try to avoid valve clearance problems, and I've still got valve clearance problems. My head gasket still isn't torqued yet, so the measurements I took are still only going to get smaller. My tightest is 83 thousandths of an inch. I'd need no less than an additional 30 thousandths of an inch to make adequate valve clearance. I might be able to drive it just fine to the corner store and back, but the minute I get her hot or over rev it just one time, it's all over. So with this valve train and camshaft background behind us, how do I go about fixing this valve clearance problem? The knee-jerk reaction is to use a thicker head gasket. I'll let Jamie explain this one.
If you have too much compression, never use a bigger head gasket to compensate, because what happens is you create a very large gap between this area and the deck of the block, and that type of quench area being big like that actually promotes detonation. So you lowering the compression a half a point with a bigger head gasket can actually give you more
knock.
detonation.
Yeah.
So tune around the compression. Don't try to delete the compression. Compression is a good thing. It's working like a charm in mine. Even with the 1.6 head, the valves are really shrouded. Half the intake, or a quarter of the intake valve, is shrouded by this piece right here.
And you know what? He's totally right. You get a double whammy when you install a thicker head gasket. One whammy would be increasing the size of the quench area, like he described. The quench area resides between the combustion chamber wall and the beginning of the pentaroof combustion chamber angles on the cylinder head. It's a flat region that claps the fuel mixture towards the center of the combustion chamber just prior to ignition, when the piston rushes towards top dead center. It squeezes the charge together for a better burn. When you enlarge the quench area, you quiet that clap at the top of the combustion chamber, making it do less than it would under normal circumstances. The other whammy is that no matter what head gasket material you use, it has a rolled steel fire ring. It's not a cast iron or cast aluminum material that dissipates heat easily. In fact, the gasket behind it, no matter if it's MLS or a composite material, acts as an insulator, trapping that heat in. So when a thicker head gasket is utilized, it enlarges the size of that fire ring and makes it a more substantial part of the quench area. This contributes to hot spots that cause knock. So I'm not using a thicker head gasket to correct my problems. Another option would be to take the cylinder head back to the machine shop for yet another valve job on top of a perfectly good valve job to recess the valves further. When you recess the valves, you change the seat pressure because whatever depth you recess the valves to also recesses the groove that the keepers sit in on the other side of the valve. You could shim the springs to correct this, but you'd need to shim every single spring. It also changes your rocker angle so that the pads on the rockers no longer sit flat and dead center on the tips of the valves. This can be fixed by grinding the tips of every single valve down, or you could just shim every single lifter to change the rocker angle. Either of these solutions would work to correct only half of the problems created by recessing the valves, but that's a lot of measurement and expensive, complicated machine work. I wouldn't do this unless I absolutely had to do it. One thing you could do is to change your valve timing, either by replacing the cams or by changing their installed center lines. Let's try that method first. These aren't really what you'd consider radical camshafts because they don't offer more lift than a stock cam. They just make more power as a result of having slightly increased duration and because of how quickly they open and close the valves. The bigger exhaust cam helps to spool the turbo quicker, making up for that tight lobe separation angle so that it can recover some of that low speed drivability. What HKS did to make up for the idle quality problems associated with tight lobe separation is to grind more of the overlap out of the clearance ramps of the cam lobes. These cams actually have less overlap than the stock cams do, and that should in theory lend to a smoother idle, but what it leaves me with is very little wiggle room on my adjustments before I have no overlap at all. I only get 4 degrees of overlap to play with, 2 degrees on either cam. At that point, I still may not get the 100,000ths of an inch valve clearance that I need to clear the pistons, and I really don't want 0 or negative overlap on this build, so first I'm going to see where my exhaust adjustments put my valve clearances, and then I'll adjust the intake cam accordingly. I advanced the exhaust cam 6 degrees because I need to make up 27,000ths of an inch, and I hope this makes it. Of course, the only way to know for sure is to repeat the valve clearance tests, but that's about as far as I want to go with it. The farther you go from top dead center, the faster the piston starts moving, and the greater effect each degree of adjustment makes on your swept combustion chamber volumes, which is why I'm cutting myself off at 6 degrees. Well, I didn't make it. Also, remember the head gasket isn't crushed yet. The head bolts are just hand snugged right now, so there's about 10,000ths of an inch to be added right back onto those numbers once that occurs. Even though I can't adjust enough clearance into my valve timing events to satisfy my quest for power, you can see the effect that's created on your valve clearance by making valve timing adjustments. This illustrates how valve timing adjustments are one of the ways you can deal with the problem that is valve clearance. Just realize that any adjustment you make changes how much of the stroke is being used for making compression, and that's precisely the reason why lobe separation angle factors we discussed earlier do what it is that they do. Just for giggles, I'm going to go ahead and advance the intake cam 4 degrees, mark up the degree wheel, do the math, and show you how the lobe separation angle is affected. 4 degrees advance should leave me with 2 degrees of overlap, but that overlap occurs while the piston is still moving upwards rather than when it's at its peak changing directions. Even though that's not ideal, this is how I'd set the intake cam if my exhaust adjustments worked. When you advance the intake cam, you decrease the intake valve clearance. We saw that advancing the exhaust cam 6 degrees only gained us about 25,000ths of an inch. I've got more than 80 thousandths more than I need already on the intake valve, so 4 degrees of advancement isn't really going to be enough to hurt anything. I'm not even going to do an intake valve clearance test. I'm just going to dial in the events on the degree wheel so that we can do the math for this example. After all, this is actually the reason Jamie gave me this car. It was so that I'd eventually be forced to rebuild it and see what he did so that I could share it with all of you. He doesn't have the time or equipment to build this audience and to share it with you himself, but he sure has the subject material, so he gave me this Hyundai instead. Thanks a lot, Jamie. This is the single most difficult video I've ever had to make. I'm not kidding. I hope that anyone new to valve timing and valve clearance can understand this example and greatly accelerate their learning curve and experience. I've seen a ton of camshaft degreeing videos, but none that explain how to deal with lobe separation angles or changes in engine behavior or problems that arise as a result of changing your valve timing. Adjustable cam gears are not fashion accessories for your engine. They're your best friend or your worst nightmare depending on how you use them, and there is no in between. If you install them in your car without removing the engine and doing these tests first, you're probably making a huge mistake. Know what effect they have on your engine and how to use them properly if you're going to use them. I hope I can help prevent at least one person from making a mistake with this car's example. That's also what Jamie would want. Of course, if you know all this info already, hopefully you at least find this entertaining. Now that we've got our cam timing events all dialed in and marked on the degree wheel, let's head over to the whiteboard again and make sense of all these numbers using the same simple equations I showed you earlier. First we get our timing events. Then we add each open and closing event to 180 and get duration at 40 thousandths lifts. HKS said use 1 millimeter or 40 thousandths on these cams. Divide by 2 to get your cam center lines. This is the center line of the cam grind. Watch out for manufacturers like HKS that print this value as the installed center line. It's not. Next we subtract intake opening and exhaust closing events to get the installed center lines. Finally we add the two installed center line values together and divide by 2 to get the lobe separation angle. 111.25 plus 96.5 divided by 2, that's 103 7/8 of a degree of lobe separation from the exhaust to the intake cam. So we gained about 1 1/4 degrees of lobe separation angle. It doesn't seem like much, but when you think about how this is a range of only 20 degrees total, that should change many of those factors we discussed by about 7%. Small adjustments yield big results. Once your cams are dialed in to manufacturer's specification, it's a little bit easier to play with these numbers and figure out what they're going to do. Knowing these numbers helps you determine how much wiggle room you have to play with if you need to fine-tune these parts later. So my problem still remains, not enough valve clearance. The thicker head gasket option is out of the question. The valve job is out of the question. The valve timing adjustments didn't do the trick and would also need the help of something else to make adequate clearance. So there's really only one option left, and it requires basically taking most of this thing right back apart. Fly cutting the pistons to fit your valvetrain is always the best option. It lets you maintain your engine's original quench area specifications, valve timing events, it lets you keep the head gasket you already bought, and it gives you what's necessary for thermal expansion, valve bounce, valve float, and rod stretch. Sure, you gain a little bit of dish volume on your pistons, and it's true that lowers your static compression, but it fixes the valve clearance issue without all the problems that are created in all of the other methods. Of course, you can't just hand them to a machinist and say, I need these things fly cut X deeper, and expect them to know where to cut it. It helps to give them a valve angle, the size of the valve that you're using, and how far off you are. But it helps the most if you can mark up the pistons to guide them where they need to be. Put your head gasket away. You want to get this right the first time, so you should jig up the valves that you wish to have fly cuts enlarged for with your test springs on the workbench. Use 3 layers of masking tape across the block to protect the deck surface, just to let you know that's 13 thousandths of an inch thick. Clean all the oil off the tops of the pistons and scrape any stubborn carbon out of the old fly cuts so you'll be able to see your marks. And then coat the top of the piston with a water-based paint, marking dye, or Sharpie. Whatever you happen to have that lets you easily scratch it away but it won't wipe off. Wipe any oil off the valves from the deck surface of the cylinder head. Set up your dial gauge and find true top dead center. Set the head back on the block, then press down on the valves and turn them. Remove the head and you'll find the valves left marks on the piston faces to indicate where they're centered. That's what your machinist will need to match when he's making his cuts. You need your clearance enlarged wherever that mark might lie. Don't take your fly cuts for granted. Just because they're there, it doesn't mean that your valves are using them. Right here you can see mine are plenty deep. The fly cuts just don't line up with the valves at all. That can be caused by a number of different things, all of which I'm sure these parts are suffering from, but there's plenty of meat here for me to fix this. I don't actually need deeper fly cuts. I just need them moved out closer to the cylinder walls. So hopefully these marks along with my valve train specs will help that to happen. I have a variation of 8.5 thousandths of an inch in piston to deck height. I'm measuring the tallest and the deepest pistons, so I'm moving the test springs over to number 2. While I was at it, I managed to launch a keeper into my air conditioner. I told you these things like to do that. Drop everything and find these things immediately whenever that happens. Each passing second makes them slip further away until they're gone forever. I could mark all 4 pistons, but if there's any variation in where the valves line up, this gives my machinist both sets of marks to help him set up his cut. I'm making up for the unmarked ones with a box of donuts anyway, so I know I won't hear any complaints. You don't usually have a lot of depth to the face of the piston to play with, so you want to have as little cut off as possible to make up that gap. Normally it's pretty easy to get away with 30 or 40 thousandths. Some pistons might let you go a whole lot further. If you run out of room for those cuts, your option is to buy a new set of pistons, and that will require that you punch the block out again to fit them. This block's already 30 over, and that's as far as I let it go on a 4G63 because the cylinder walls start getting too thin between the cylinders, and that's when things start to heat up. So this is its last chance for greatness. When this thing finally blows up, and I look forward to it, the whole bottom half is getting replaced. Sure, it stinks to have to take it right back apart again in order to fix the valve clearance problem, but it's the right way to do it. It would have been really bad news if I didn't. The 4 options to fix valve clearance are from worst to best: head gasket, valve job, valve adjustment, piston work. Those are your options. If you're building your own engine, it's your responsibility to make sure that these things are right. Make this test part of your camshaft install because it will ensure that you didn't build a grenade, and it will tell you what you need to know later when you're tuning it. I'm really looking forward to the next episode, mostly because I don't have to narrate it. I've now covered all the most important stuff to consider about valve train geometry when you're building an engine, and explained the pros and cons for doing it this way. These fly cuts should do the trick to give me the clearance I need to help me make the most of my port work and camshaft selections. So now that this last major obstacle is cleared, it's time to make this thing run again. Thank you, Jamie, for this opportunity, and of course for the Hyundai. I'm grateful to every last one of you who've chosen to share this experience with me, and can say without any hesitation or doubt that all of you helped make me a better mechanic. Be sure to click things, click all the things, click lots of things. That's what the internet's for. And until the next episode, stay tubed.